Hi, welcome to Chem with Chem. In this session, we're going to be doing a medley of electrolysis questions. These questions span the last 10 years, well, depending on when you're watching this. The electrolysis question for the May-June 2021 sitting is not in this medley, but you can view that by just checking out the link below. That's in the description. You will find the entire paper worked there. So let's get right into it. If this is your first time to the channel, welcome. And of course, consider subscribing, check out all the material that is here. And of course, be sure to leave a like, share with a friend, and consider subscribing. Now, when we are going into electrolysis or any new area, there are some jargons that we have to understand. It's like in law, law in and of itself is a whole, language. There are jargons that are just used that are just unique to that area. Mens rea, actus rea, and so on and so forth. Same thing for any other discipline, accounts and so on. Yes, for chemistry in general, we have that, but for electrolysis, there are just some terms that we have to understand. We're not going to look at all of them, but some that we don't look at here at the beginning will come up a little later on. So we have a little activity that we're beginning with. That we're going to be, it's like word meaning, we're going to be matching the definitions with the terms that are here. And the first one is done for us. The terminal at which electricity enters or leaves the electrolyte. That's called the electrode. So these are rods that allow electricity to enter and leave the electrolyte. And then the other one, the one that follows, one up next, a charged particle. A charged particle would be an ion, and then a negatively charged particle. So cations are positively charged. So we've done ion already. Cations are positively charged, and ions are negatively charged. So this would give us an ion. Then we have the negative electrode. The negative electrode is, so we've done an ion. The negative electrode is the cathode. Chemical change, which is the result of electricity passing through an electrolyte. So that would be electrolysis. That's what electrolysis is all about. Looking at the word electrolysis, we should be seeing electricity. We should be seeing the word lysis, which means to split. A positively charged particle. So we looked at a negatively charged particle earlier. So a positively charged particle would be a cation, which are positively charged cations. The positive electrode is the anode. How many have you gotten so far? Then a substance which can conduct electricity in its molten or dissolved state. That would be an electrolyte. And the container in which an electrochemical reaction takes place, that would be the cell, right? The entire setup, the container in which the electrolyte is and electrolysis is taking place. And the last one, for a voltage which drives current around a circuit in one direction only, the last one would be DC voltage. Right, not able to write it in, but that one would be DC voltage. Can get that in. So completion, so that would be DC voltage. That does it for this section. So for this part B of the activity, the language of electrochemistry, we have another matching activity. We have a diagram this time showing the setup of the apparatus that would be used for electrolysis. So we're just going to write on, we're just going to label. All right, so This part here is representing DC voltage based on what's given. That's where we'd have our cells or our batteries, or the batteries connecting cells connected in series, or just the power supply. So DC voltage would be there. The part we always look for the part with the long stroke. That part is the positive side. And to that part, we normally have our positive electrode connected, which is our anode. So if we trace this coming around, if we trace this, then we should label this as our anode, right? There's no switch on this. There's normally a switch. And we could also have a light bulb. And of course, when electricity passes through, then we could have a switch as well. When electricity passes through, the bulb will glow. So if that's our anode, over this side is our cathode. In the container itself, in the cell, we would have our electrolyte. And this would be our cell, the actual container that the chemical change is taking place in. So that is it. So those are the most of the terms that we will come across. Of course, if we're linking, we need to look back to our acid-base salts, because when we're thinking about electrolytes, the same substances that are acids, they are electrolytes as well. So our strong acids, strong alkalis, they form strong electrolytes which have many ions present that will carry a current if a voltage is applied. Or weak electrolyte, or weak acids and weak alkalis, those would make weak electrolytes as well. All right, so we're moving on now to the first question. This one is from the May-June 2018 paper. As I said earlier, the other one, if we're going backwards, would be from May-June 2021, but that one can be found in the link in the description below this video. All right, so May-June 2018, question 4. The circuit in figure 3 can be used to test if a substance conducts electricity. This should be one of the common experiments that you do, properties of ionic and covalent substances. So we have our power supply, we have our bulb, power supply, bulb, we have the empty container, which we just called a cell earlier. We have electrode 2 and we have electrode 1. And we know that they just call them generic terms, electrode 2, electrode 1, which means they're not giving us any hints. We should actually know what those are. So they ask us in part A for 2 marks to define electrolysis. So we will just be thankful for two marks. All right, so it's the decomposition of an electrolyte by the passage of an electric current. Part B, describe the effect that each of the following substances will have on the bulb when the substance is placed in the empty container in figure 3. State a reason for your answer for each substance. So the first one is solid sodium chloride. So what effect will this have on the bulb? So if it's solid sodium chloride, then it's safe, it's correct to say no effect. And the reason here, this is an ionic component, it's in the solid state, so all the ions are involved in bonding. We could say no free ions present. We need free ions present to actually carry the current when a voltage is applied. And then 1 mole per dm cube hydrochloric acid. So the effect is that for this one, the bulb will glow. And the reason this is a strong acid, so this is an aqueous solution containing H plus ions and Cl minus ions, as well as H plus and OH minus ions. But strong acid, so ions are present. As it ionizes fully to produce ions. And then for this one, ethanol, we expect no effect on the bulb. So ethanol is a molecular or a covalent substance. It's a molecular compound which does not dissociate into ions. And then they said if we have a bar of lead touching the electrodes, we would expect the bulb. So the bulb will glow in this case. So the bulb glows, and the reason is so I'll just put my reason here as I'm not able to write it in the section for reason. So the reason is it's a metal. So mobile electrons are present to carry the current. Remember what happens in metallic bonding, we have cations embedded in a sea of mobile electrons. So in that bar of lead, we'd actually have lead 2+ ions embedded, lodged or stuck, as what students would say. I just showed one layers, but this part here would be representing the mobile electrons. So if a voltage is applied, then the electrons will move, and just label. So the electrons will move and carry the current. So part C, for 5 marks to make this 15, a sample of molten lead bromide, that's PbBr2, is electrolyzed for 3 minutes with a current of 6 amperes. Calculate the mass of lead that is deposited at the cathode, given that 2 moles of electrons are required to liberate 1 mole of lead, as shown in the following equation. All right, so we have the equation we're seeing where, just to make it, more, just to get better resolution. Pb 2+, which is a liquid, plus 2 moles of electrons liberate or produce 1 mole of lead. And they've given us the formula Q equals IT, the quantity of electricity is equal to the current strength in amperes times the time, how long the current passes or flows for. All right, so we want to find now the mass that would be obtained if 6 amperes flow for, what's the time? For 3 minutes. So what we're going to do, we're going to over this side just work out the quantity of electricity associated with 3 amperes flowing for 3 minutes. So Q equals IT. So Q is the current strength in amperes, that's 6 amperes times 3 minutes. 3 minutes in seconds will be 3 times 60, which is 180 seconds. So it's 6 amperes times 180 seconds. And we just need to get that down. So that is equal to 1080 coulombs. All right, so we're going to go ahead and use the equation that we have here. This is saying that 2 moles of electrons, which is the same as 96,500 coulombs times 2, because it's 2 moles of electrons. So when 96,500 coulombs times 2, because it's 2 moles of electron flow, we end up with 1 mole of lead. 1 mole of lead has a mass of 207 grams. So that's the amount of lead that is produced. Now, if we have our 10, well, before we even get to the 1080, we can rewrite this. 96,500 times 2 is 193. So we're saying then, let's use a different color to start first. So 193,000 coulombs. We're saying it required that amount of electricity for the liberation of 207 grams of lead. So if we used 1080 coulombs, what amount of lead are we expecting? So we're solving for X. So when we do that, we'll end up with 193,000 X is equal to 1,080 coulombs times 207 grams. All right, this is coulombs here. Divide both sides by 193,000 coulombs to make X the subject. And when we do that, we'll end up with, so that's 1080 divided by 193,000. And then whatever we get, we multiply it by 207. And we'll end up with X being equal to 1.16 grams of lead. And that will give us our 5 marks. So we have the first 15 marks down. So this is May-June 2017 question 2C. This is the part that deals with electrolysis. Ethanoic acid is known to be an electrolyte. Define the term electrolyte. So an electrolyte is a molten or aqueous substance that allows
current to pass through.
Identify the ions that are produced from ethanoic acid during electrolysis. So the ions that we would get from ethanoic acid would be the ethanoate ion, that's CH3COO minus. Aqueous ions, that's the ethanoate ion, would also get H plus, and we would get OH minus ions. Don't need to say H plus twice. Define the term cathode. So the cathode is you could say that it's the negative electrode, or that is fine, negative electrode. Or it's the rod connected to the negative terminal of the battery, or the rod connected to the negative terminal of the power supply. Predict which ions from C2 above will migrate to the cathode. So the cathode is the negative electrode, so we know opposites attract. So the only ions that will migrate to the cathode in this case would be the H plus ions. Cathode is the negative electrodes, so the positive ions here will migrate to it. Then they're asking, is ethanoic acid a strong or weak electrolyte? So ethanoic acid is a weak electrolyte. And they're asking us to explain our answer. So we'll say it's a weak acid which partially ionizes. That's kind of redundant. It partially ionizes in water, liberating few. This is very redundant. Few ions. So a weak electrolyte. So as we had mentioned earlier, strong acids will be strong electrolytes because many ions are present. All right, weak acids will be weak electrolytes because when they liberate only partially or incompletely, they ionize incompletely to produce very few ions. So few ions will be there to carry an electric current. All right, so this one is May-June 2014, question 4. And we're just going to write the answers to the side. Magnesium and sulfur are two elements in the same period of the periodic table. That's period 3. The oxides of these elements show different properties as presented in table 2. So we have the melting point and we have their state. All right, that would be their state at room temperature. All right, so the oxide of magnesium, MgO, oh my God, it's 2852. And the oxide of sulfur is negative 70. The melting point is negative 72 degrees Celsius, and that's a gas, while the magnesium oxide is a solid. So with reference to the bonding, account for the differences in states and melting points of the oxides of magnesium and sulfur. So for MgO, magnesium oxide, we're going to talk about the bonding. So the bonding present is ionic bonding. Ionic bonding, so MgO contains ionic bonding, which means that we have a very strong electrostatic, okay, right? Very strong electrostatic forces of attraction holding the ions together. Very strong electrostatic forces of attraction, because we're talking about ionic bonds. And because these forces of attraction are so strong, it means that the substance would, well, because the forces of attraction are, so it's an ionic bond. So for one, it's an ionic substance. So for one, there will be solids. They tend to be solids. So these strong forces of attraction hold the particles together in a regular 3D arrangement. We have an alternating we have cations and anions alternating, giving us this 3D structure. But the point though is that the forces of attraction is extremely strong, resulting in the particles being in the solid state. So strong forces of attraction, they are held together in a regular fixed manner in the solid state. And then the melting point is high, 28,500, because we have such strong forces of attraction. Large amounts of energy is required to actually break or to melt the substance. So these strong forces of attraction, strong forces, or these strong electrostatic forces of attraction mean that lots of energy is required to break these forces of attraction, that is to melt them. All right, so that's why the melting point is so high. Now, on the other hand, for the oxides of sulfur, they would contain covalent bonds. That's for one, but then not just that. For it to have such low melting point, we're not talking about the actual covalent bond that's present between like the sulfur and the oxygen itself. We're talking about the forces holding one of the molecule to another molecule. So though there is covalent bonding, between the atoms in the oxides of sulfur, the overall molecules are held together by weak intermolecular forces of attraction. So for one, we'll state that this is the oxides of sulfur. So the oxide of sulfur, they didn't really say if it's sulfur dioxide or sulfur trioxide. So I guess we can just call it SOX. So the oxides of sulfur, it's a covalent compound, but not just a covalent compound. It's a simple molecular compound. So we'll change that. So it's a simple molecular compound, and they are held together, each molecule, they are held together by weak intermolecular forces of attraction. So these forces of attraction are very weak. These forces of attraction are very weak. These forces of attraction are very weak. They're not strong enough to actually pull the molecules together. So molecules are the oxides of sulfur. Molecules of the oxides of sulfur are in the gaseous state. So very little energy would be required to break them apart. Those forces of attraction are already weak, so they're not strong enough to bind or to hold the molecules together. So it would require very little energy to actually break them. So at room temperature and pressure, you'd find that they exist as a gas. And furthermore, to melt them, it doesn't take that much energy because it melts at negative 72 degrees Celsius. For part 2, explain whether the oxides will conduct electricity, and if so, under what conditions. So The magnesium oxide, so MgO, will conduct electricity, but only, so I'll just state it, conducts electricity only when molten. All right, so in the solid state, all the ions are involved in bonding. All the ions are involved in bonding, but in the molten state, the ions are set free. All right, so kind of over explaining here, we just need to state that the magnesium oxide is an ionic compound. So in the solid state, all the ions are involved in bonding. Explaining, so it's fine. But when molten, the ions are set free and would be able to carry a current should a voltage be applied. The oxides of sulfur, SOX, we don't know if it's sulfur dioxide or sulfur trioxide, these will not conduct electricity in any state. These are covalent substances, so they don't have any ions present, so they will not conduct electricity under any state or under any conditions, we should say. So that should give us the 10 marks. All right, 4 here plus the 6 earlier. Part B, figure 5 is a diagram of the apparatus proposed by a group of students to investigate whether aqueous lead nitrate, ethanol, and aqueous ammonia would conduct electricity. All right, so we're examining the diagram. Part 1, why is the circuit as represented in figure 5 not suitable to achieve the aim of this experiment? All right, so for one, if they're going to be checking to see if something conducts electricity, this diagram as is not suitable. They would not have anything. There's nothing there to show. There's nothing there to give them an indication that something is conducting. So what they need a lamp. So the lamp, not like a kerosene lamp, the lamp, or what we call the bulb, is missing. All right, modify the diagram to produce a circuit that is suitable for achieving the aim of this experiment. So we would need to put in the lamp, and of course, if something is conducting, then of course it would glow. And not to over answer, but we would need our cell, and in the cell we would put the different liquids. All right, I think that goes without saying. Modify the diagram. So we've modified the diagram. Classify the 3 substances to be investigated: aqueous lead-2 nitrates, ethanol, and aqueous ammonia, either as conductors or non-conductors. So lead-2 nitrate, aqueous lead-2 nitrate, that is an electrolyte, that's a conductor. And then ethanol, we saw in an earlier question, is a non-conductor. No ions are present there. And aqueous ammonia, NH3 aqueous, this would be a conductor. Though a weak conductor, it's a weak electrolyte, so it ionizes partially, but it will produce some ions, so it will conduct. Not as much as lead nitrate, but it will conduct. We're just classifying as conductors or non-conductors. So there we go, another 15 marks. This is January 2014, question 2, another electrolysis question. The process of electrolysis has a number of useful applications. During the purification of copper by electrolysis, special electrodes are used to give the desired products. Define the term electrolysis, right? We give thanks for small mercies. It's the decomposition of an electrolyte by the passage of an electric current. So electricity, lysis, to split. So it's pretty much splitting up of the electrolyte using electricity. So whereas bonding is marriage, electrolysis is divorce, or what we call compound divorce. State the type of anode that is used in the purification of copper. So in the purification of copper, the anode will be the impure copper. The impure copper would go at the anode for the purification of copper. Part B. Figure 2 depicts the apparatus that is used to electrolyze a sample of molten lead-2 bromide. You see our apparatus, electrode 1, electrode 2. Electrode 1 is connected. Well, they have a plus over electrode 1. So we should be thinking of anode for electrode 1 and cathode for electrode 2. Which of the electrodes 1 or 2 in the diagram is the cathode? So the cathode is the one with the negative sign, or the one attached or connected to the negative terminal of the battery or the power supply. So electrode 2 would be our cathode, right? The formula of the ion that migrates towards the anode. I like what they're doing here. Don't let them trick you. So we're looking at molten lead-2 bromide. So we'll have Pb2 plus liquid, and we will have Br minus liquid. So the anode, whenever I see the word anode, normally put a plus beside it to remind me that we cannot put, something with a positive charge over at the anode. So the ion that will migrate to the anode would definitely be the Br minus liquid ions, and they want a balanced equation for the reaction occurring at the cathode. So they're now switching it over. So the cathode is the negative electrode. So it means that our positive ions will migrate towards the cathode. And when they migrate towards the cathode, they will gain electrons because reduction occurs at the cathode, right? So we just need to show electrons being gained here, and this will give us Pb. It will still be dripping off the electrode as a liquid. So that is it. Pb2 plus liquid plus 2 moles of electrons to give Pb liquid. Part 4. A current of 5 amperes is passed through the molten lead bromide for 5 minutes. Calculate the mass of lead that would be deposited. All right, so we're going to use the equation that we just wrote, which states that Pb2 plus liquid plus 2 moles of electrons to give Pb. All right, so from this, we're seeing where 2 moles of electrons and 1 mole of electron is the same as 1 Faraday, 96,500 coulombs per mole. So from this equation, we can write that 2 times 96,500 coulombs, 96,500 coulombs is required for the liberation of 207 grams of Pb, because Rm of Pb is 207, which means that the molar mass is 207 grams per mole. So we're going to come back to this. So in essence, we're saying 193,000 coulombs, that's 2 times 96,500, that is required for the liberation of 207 grams of lead. So we're going to work out the quantity of electricity that we'll get when 5 amperes flow for 5 minutes. And they did not give us the formula, but we know that Q, quantity of electricity, is equal to IT. I is current strength in amperes, so that would be 5 amperes times, and this is 5 minutes. So we'll convert the minutes to seconds by multiplying by 60. So we'll end up with 5 amperes times, that's 5 6 30. That's 300 seconds. So that's 5 amperes times 300 seconds. Ampere seconds will give us coulombs. 5 3 is 15. So that would be 1500 coulombs. So we're going to take this now and put it in our equation over here. So we have a statement. 193,000 coulombs liberate 207 grams of lead. So what if we used 1500 coulombs? What mass would we get? So once we solve for x there, we are good to go. That's all we're required to do, and that will give us our 4 marks. So x then, solving for x, making x the subject, is going to be equal to 1500 coulombs times 207 grams, all of that over 193,000 coulombs, and whatever we get is our answer. So that's 1,500 divided by 193,000, and then all of what we get there times 207, and that would give us 1.61 grams of lead for 4 marks. 2 experiments were set up as shown in figure 3. All right, so we have zinc rods immersed in experiment 1 in magnesium sulfate, and in experiment 2, zinc rod immersed in copper sulfate. That's aqueous copper sulfate, aqueous magnesium sulfate, right? In experiment 1, no visible change was observed, while in experiment 2, a brown solid settled to the bottom of the container. So let us explain the observation for experiment 1. So this is checking our knowledge of the reactivity series. So let's see if we can remember it. We don't have all the elements present, the metals present, so that is it. So we don't, there are no visible change was observed in experiment 1, no visible change was observed. So we're going to explain that. In a sense, we're checking to see if zinc is able to displace magnesium from its compound. All right, so no visible change was observed, and we expect that. Well, that's what we got, or that's what they got in the experiment. So we just need to state here that zinc is lower in the electrochemical series or the reactivity series than Mg, so would not displace magnesium, Mg, from its compound, right? And that will give us the full marks. And just to keep everything together, we're going to explain what we got in experiment 2. In experiment 2, a brown solid settled to the bottom of the container. So let us look at where. So we need to look at where zinc and copper are relative to each other. So zinc is here. Okay, fix that again. So we're going to look at the relative position of zinc and copper in the electrochemical series. So zinc is here and copper is here. So zinc is above copper in the electrochemical series or in the reactivity series of metals. So it displaces or takes the place of copper from its compounds. So the brown solids that we see, that's copper falling out of solution. So they don't really ask us for the equations or anything. So the brown solid would just be copper falling out of solution because zinc would have taken its place. We don't need the equation for this one. So it's zinc, just to explain. All right, so zinc will now go into solution as zinc sulfate. And copper would be left standing alone, falling out to the bottom of the container. That will give us the full marks. Now, this is question 5. Well, May, June 2013, question 5. All right, and this figure 5 is a diagram of a cell used in the industrial preparation of chlorine by electrolysis. So this would have to be concentrated sodium chloride solution that we're using You might see that being referred to as brine, mackerel in brine, tuna in brine. That's just a preservative. One of the uses of sodium chloride concentrated solution is used to help to preserve meats on a whole. All right. So figure 5, this is the diagram of the cell used in industrial preparation of chlorine by electrolysis. Part A, outline the industrial preparation of chlorine using a cell such as the one shown above in figure 5. Include in your answer the name of the electrolyte and the ions present. So part 1, so the electrolyte is concentrated NaCl solution. The ions that would be present are aqueous, Cl minus aqueous, H plus aqueous, and OH minus aqueous. They want an explanation for which ions are preferentially discharged at the electrodes. So, of course, it's concentrated sodium chloride. So normally OH minus ions would be liberated, right? Because it's at the bottom of the electrochemical series for anions. But in this case, there's a relatively larger amount of chloride ions than OH minus ions. So Cl minus ions would be liberated preferentially as it's in a relatively higher amount. So Cl minus would get the nod at the anode because it's present in a relatively larger amount, or relatively higher amounts, or concentration. All right, and then they want an explanation for the ions that will be discharged so this time it's at the cathode. So we have a toss-up between H plus and Na plus. So H plus would be liberated preferentially at the cathode, all right? And despite you having a larger amount of Na plus, it requires less energy for H plus to be liberated. All right, still requires too much energy for the Na plus to be liberated. So H plus would actually be liberated. And the role of the ion exchange membrane in the diagram is to prevent the products from mixing. So as we see over here, chlorine is liberated over here, hydrogen is liberated over here. So the membrane prevents these two from mixing. We don't want the products to be mixing. All right. So just going to bring up part B so we can zoom in and get where to work this one out. And we jumped the gun a while ago. We did not do the ionic equation showing the reactions at each electrode. So at the anode, chlorine would be liberated at the anode. So we put in a plus there. So remember that it's positive. So we'll have Cl minus, well, two of them, aqueous, to give Cl2 gas plus 2 moles of electrons. That's what's happening at the anode. And at the cathode, we would have 2H plus aqueous gaining those 2 electrons to give H2 gas. So that's what's happening at the cathode, both electrodes. And we gave the role of the ion exchange membrane in the diagram. It's to prevent the mixing of the products. So here, an experiment, so part B, an experiment was carried out to purify copper by electrolyzing copper sulfate solution using the impure copper as the anode and a pure copper cathode. State what is expected to happen to the anode during the experiment. So the anode is supposed to disintegrate, all right? Or it's supposed to just get smaller and smaller as time progresses. calculate the mass of pure copper that would be produced during the experiment if a current of 5 amperes flowed for 30 minutes. So part 2 of B. So we'll need more space for this. Now, we will need, so this is the electrolysis of, well, copper sulfate, or a purified copper in this case. So we're looking at what's going to actually happen at the cathode here, the mass of pure copper that will be produced during the experiment. So at the cathode, remind ourselves that the cathode is the negative electrode. So we would actually have Cu2 plus ions going there, equals, they will gain 2 moles of electrons, or we require the passage of 2 Faradays, and this will give us copper, Cu, that's S, solid. All right, so that's the equation. Now, this is saying, and we've worked this before 2 times, so from this we can write that 2 times 96,500, which is 193,000. Okay, let's try that again. Let's make it more, see if we can get it clearer. So it means 193,000 coulombs is required for the liberation of 64 grams of Cu. So we're going to use the amperes that they give us and the time that they give us in minutes to actually calculate what our quantity of electricity is. So 30 minutes is equivalent to 1800 seconds. So the quantity of electricity, Q equals IT. So we're going to use 5 amperes current strength times, and this is 30 times 60. We're converting the 30 minutes to seconds. So that will give us 1800. So it's 5 amperes times 1800 seconds, which will give us 9,000 coulombs. So we're going to take this now and solve for the mass of copper that will produce. So the 9,000 coulombs will give us X grams of copper. When we solve for X, X is equal to the 9,000 coulombs divided by 193,000 coulombs times 64 grams of copper. And when we do that, we'll end up with 2.98 grams of copper. And that would give us 15 marks. So another 15 marks. So this is January 2013, question 4. Part A, explain why magnesium conducts electricity when solid, but magnesium iodide, that should be MgI2, only conducts electricity when molten or in solution. So first things first, magnesium is a metal which has cations embedded in a sea of mobile electrons. The electrons are able to move and carry a current when a voltage is applied. All right, so for electricity, for something to conduct electricity, it must contain ions or electrons, because electricity is really a movement of charged particles. So the metal has mobile electrons, or what we call the sea of mobile electrons. So if a voltage is applied, the electrons will carry the current. Magnesium iodide now, it contains ions, but in the solid state, all the ions in magnesium iodide are involved in bonding. They're locked up in bonding. However, in the molten state or in aqueous solutions, these ions are set free. And of course, if they're set free, they can move and they can now carry a current when a voltage is applied. Again, for electricity to be conducted, there must be free ions or free electrons. That's it. So you can rewind and put that in your own words. Part B, draw a label B1. Draw a label diagram of apparatus which could be used in the electrolysis of molten magnesium iodide. So we get to draw, we saw the electrolytic cell earlier. So we're just going to, this is fine. So putting in a switch. This is fine, this will do it. So this is the MgI2 liquid, that's the electrolyte. So this is fine. So this is the label diagram. 2 marks for this. Part 2, write equations to indicate the chemical reactions which will occur at each electrode. So part B, 2, so it's molten magnesium iodide. So the ions present are, okay, the lead question is still in my mind. So the ions present are Mg2 plus liquid, and we have I minus liquid. So let's look at what happens at the anode. So since loss is taking place, let's look at that one first. That's what's producing the electrons. So that's the positive electrode. So we'll have the negative ions there, I minus liquid, to give I and a mole of electron. But the moment this happens twice, the atomic iodine, they combine to give us molecular iodine, which would require 2 on the left, 2 iodide, 2 moles of electrons. All right, so the iodine in this case, this would be in the form, the iodine here, we're talking about molten magnesium iodide. So the iodine here could come off as a vapor. So we could put, and that's just because of what's happening. It could come off as a vapor. So we would get the iodine in this case coming off as a gas, right? Electricity is flowing, will break down the bonds between those iodine molecules. Those are weak intermolecular forces, so we'd get iodine coming off as a gas. All right, so that's what's happening at the anode. At the cathode, which is the negative electrode, we would have magnesium ions going there, liquid, and they will gain these same 2 electrons. Right, so these 2 electrons that are just produced at the anode, they would travel over via the circuit and they would be gained at the cathode. So these are the same 2 electrons we're talking about. It's a transfer of electron process. So when this happens, we will end up with Mg solid. And the last part, part C, they're saying that a current of 5 amperes is passed for 10 minutes through the molten magnesium iodide. Calculate the mass that will be formed at the cathode. So from this, we can write 2 times 96,500 coulombs. That's 193,000 coulombs. Liberate 1 mole of magnesium, which has a mass of 24 grams. That's our statement. So we want to know when 5 amperes flow for 10 minutes. 10 minutes is the same as 600 seconds. So Q equals IT. 5 amperes times 10 times 60. That's 5 amperes times 600 seconds. 5 6 is 30. So that will give us 3,000 coulombs. So when 3,000 coulombs flow, we want the mass that is produced. So that would be equal to 3,000 coulombs over 193,000 coulombs, that times 24 grams, to give us the mass of magnesium that will be liberated. So when we do that, we should end up with, what's your answer? We should end up with 0.37 grams of magnesium. And just like that, 15 more marks. So this is May, June 2012, question 2, still on electrolysis. Figure 3 shows a simplified diagram of the apparatus used for the electrolysis of aqueous copper 2 sulfate, CuSO4, using platinum electrodes. All right, so what's very important to note is that we're using platinum electrodes, and the type of electrode being used is one of the factors that affect which ion is discharged or liberated or set free during electrolysis. All right, if we're using an active electrode, say at the anode, then that electrode would actually break down and take part in the reaction. But since we're using platinum, or if it were graphite, we know that these electrodes will just allow electricity to enter and leave the electrolyte. So they won't take part in the reaction. They're safe, quote unquote safe. First question, part A. Deduce the oxidation state of sulfur in copper sulfate. So that's CuSO4. We want to find the oxidation state of sulfur. So we'll put in the oxidation state for the other elements. All right, so the copper here is +2, and the sulfur, we don't know the oxidation state, so we'll put it as X. The oxidation state of the oxygen here, it's in a compound and it's not a peroxide, so it's -2. So we can write an algebraic expression. So we'll say +2 plus X plus, we have 4 oxygen, so it's 4 times the oxidation state of oxygen, which is -2. And all of that is equal to 0. This is an ionic compound. So the oxidation state, the sum of all the oxidation state of the different elements in this compound is equal to 0. So from this, we can just simplify +2 plus X and positive 4 times -2. This is a -2 right here, is equal to -8, and all of that is equal to 0. +2 minus 8, that will give us X minus 6 equal 0. So it means that X is equal to +6. Or you could have just written +6, you'd have got the answer without all of that, but just showing where it's coming from. At the anode, the hydroxide ions are discharged in preference to the sulfate ions. So generally, whenever we're doing an electrolysis question and we get whatever the electrolyte is, we are supposed to just write down the ions present. So it's aqueous copper 2 sulfate, so we're going to get Cu2 plus aqueous. We'll also have SO4 2 minus, that's the sulfate. We'll also have H plus from water and OH minus from water. So they're saying at the anode, we know the anode is the positive electrode. So at the anode, OH minus and sulfate will both migrate, but only the OH will be liberated preferentially. The OH will get the nod. And they want a reason for this. And the reason is simply because OH minus ions is lower in the electrochemical series of anions. So for the electrochemical series of anions, we have carbonate, sulfate, nitrate, chloride, bromide, iodide, OH minus. So those at the top, they form more stable compounds, so it's harder for them to break apart. So those at the bottom now, the compounds they form, they are not so stable, so it's easier for them to be discharged or to be broken apart. So in this case, the OH minus ions will be liberated preferentially, and we just need to state that OH minus ions are lower in the electrochemical series, right? And that should give us the marks there. Well, the 1 mark really. For part C, write a balanced equation for the reaction at the anode. So this is one of the few things I ask students or encourage students to commit to memory when OH minus ions are liberated at the anode. So the equation is 4OH minus equals to give 2 moles of water, or 2 water if you may, plus O2 gas. So we'll see bubbling, of course, effervescence, and 4 moles of electrons are liberated. From the equation written in C above, state whether the reaction at the anode is oxidation or reduction. And even if we cannot spot it from the equation above, we can write oxidation. And this is because we know that oxidation always occurs at the anode. So the explanation for this, we can state that loss of electrons is taking place. We're seeing that electrons are lost, electrons are generated. So we have OH minus, and on the right-hand side, we see electrons being made available. So we could say loss of electrons is occurring. Loss of electrons is taking place. We could also show that the oxidation state, another way we could show that the oxidation state of our oxygen is increasing, because over here in OH minus, the oxidation state of the oxygen is -2. That of the hydrogen is +1, it doesn't change. So the hydrogen's oxidation state is +1, it doesn't change on the right. Over here we have oxygen in the water is -2. But on the right as well, we have the molecule in oxygen, the molecule in the elemental state, that is, we have the oxidation state being 0. So we see that the oxygen's oxidation state, we could state that oxygen's oxidation state increased from -2 to 0. So we just want to make a note of that. So here we go, we're having an increase in oxidation state there from -2 to 0. So we could state that oxygen's oxidation state, another reason, oxygen oxidation state increased, oxidation state in OH minus increased from -2 to 0 in O2. And we know that an increase in oxidation state is also oxidation. For part E, we're to state 2 changes that occur in the electrolyte. And for us to really appreciate the changes that are occurring in the electrolyte, we have to, again, go back to the ions that are present. So the ions present, we're electrolyzing copper-2 sulfate. So we have aqueous CuSO4. And we deliberately writing this part in blue. And from the water, we have H plus and OH minus ions. So the Cu2 plus, the presence of this, let's just ensure that this Cu is looking like Cu. So the Cu2 plus is what gives the solution, it's the blue. All right, copper-2 plus ions in solution, they are in aqueous medium, it's blue. So in the electrochemical series of the cations, our copper falls below hydrogen. So copper would be liberated preferentially to the hydrogen. So pretty much, we would pretty much be removing then. If copper is liberated preferentially to the hydrogen, then they will be removing copper-2 plus ions from the solution. And remember that the copper-2 plus ions are what's responsible for the solution being blue. So we're removing copper-2 plus ions from the solution. So first change that we'll expect in the electrolyte is that it will decolorize as time goes by. So with time, solution here is the electrolyte. So the solution or the electrolyte decolorizes with time. Or you could say it becomes paler and paler. All right, so that's one change. Now the other thing, we have to look at what is happening what is being liberated as well, to kind of have an idea of the other change that will take place in the electrolyte. All right, so we are also removing OH minus ions from the solution, because when we stated in the previous question that OH minus ions are liberated preferentially. So when OH minus ions are removed, then the only thing we're left with is H plus and SO4 2 minus ions, and these are all aqueous ions we're referring to. So if we have H plus combining with SO4 2 minus, that will give us sulfuric acid. So it means that the solution, the electrolyte is becoming acidic in nature. It's becoming acidic due to the fact that we now have H plus combining with, so you put the H plus together, H plus with the SO4 2 minus, will actually end up with sulfuric acid, H2SO4 in aqueous medium. All right, and then for part F, for 4 marks, we're going to be doing our calculations. And once we understand the calculations, once we do a few of these or one of these, it's almost like you've done them all. It's the same principle. So we're asked here to determine the mass of copper in grams, which will be deposited at the cathode when 5 amperes of current passes through the electrolytic cell for half an hour. And they gave us the relative atomic mass of copper, and they told us that 1 Faraday is equivalent to 96,500 coulombs. And that's the quantity of electricity that flows when you have 1 mole of electrons. All right, so we'd have to write the equation for what's happening at the cathode. So at the cathode, we would state our equation there, that's Cu 2 plus ions aqueous, and they are going to gain 2 moles of electrons, and that will give us Cu solid, right? So we get marks for stating that. All right, so what does this mean? 2 moles of electrons, when 2 moles of electrons flow, that is equivalent to 96,500 coulombs times 2, right? So that amount of electricity is required for the discharge of 1 mole of copper, which is the same as, or which has a molar mass of 64 grams per mole. So that's the amount of copper that is liberated when this amount of electricity flow. So 96,500 times 2, that's 193,000 coulombs of electricity. That's what's required for the liberation of 64 grams of copper. That's our standard statement. So we want to know now the mass of copper that will be liberated or produced when 5 amperes flows for half an hour. So we'll need to calculate what's that in terms of quantity of electricity. So we'll say Q equals IT. I is current strength in amperes, which here is 5 amperes, and time is in seconds. So this will be, that's half an hour, that's 30 minutes times 60 in order for us to get that into seconds. So that's 5 amperes times, that will be 1800 seconds. And when we just need to punch that in to see what the value is. Punch that in, what do you have? So that's, that will give 9,000 coulombs. So we're going to take this now and put it in our so this, we're going to use this to solve the mass of copper. So from the statement earlier, 193,000 coulombs produce 64 grams of copper. So if we had used 9,000 coulombs, which is the equivalent, or which is the quantity of electricity we get when 5 amperes flow for 30 minutes, we want to find out the mass of copper that would be associated with. So we solve for X and we're good to go. So X here is equal to 9,000 coulombs over 193,000 coulombs, and that is being multiplied by 64 grams. All right, and then whatever we get, that's the mass that would be deposited. And this, so X here is equal to 2.98 grams of copper. And that should give us 4 marks. Sometimes we're given Q equals IT. Sometimes we're not, we just need to remember it. So quantity of electricity is equal to the current strength multiplied by how long it flows in seconds. So we have to convert the time that we're given in seconds, to seconds rather. Okay, for the remaining 3 marks, part G, indicate below how the apparatus in figure 3 can be modified to obtain pure copper from impure copper. If no modification is required, write no modification required in the relevant space. So we want to obtain pure copper from impure copper. That's purification of metals or purification of copper in this case. So you can always rewind to look back at what the diagram was. So I'm just gonna do a little sketch here just to not disrupt the flow. So this is what our diagram looked like. We had platinum anode and we had a platinum cathode, and they said that the electrolyte was copper 2 sulfate equals copper 2 sulfate. And this is the platinum anode, PT anode. And the cathode is also PT cathode. So I'm just gonna put in a plus here so we know that this is the anode, minus here, we know that this is the cathode. So we're looking at the purification of copper. So if we're going to purify copper, the anode would have to be different. We would have to use, we'll put a piece of impure anode and we'll put a piece of impure copper at the anode. So we'll put a piece of impure copper here. That's what the anode would need to be, piece of impure copper. And then the cathode now, since we want pure copper to be collected at the cathode, we would put a piece of pure copper at the cathode. So when reduction occurs, like we looked at in the previous question, right? So we know that the CO2 plus ions would be gaining electrons to give Cu, solid. The solid will be deposited on the cathode. You want the copper that is being formed here, you want the copper to be collected on pure copper. If you use platinum cathode or carbon cathode, then the copper will collect on it and then we'll have the problem of getting it off. And then you'll end up with the same problem you're trying to solve, that of purifying copper. So you'd have to use a piece of pure copper at the cathode so that more pure copper can be collected on it. And then the electrolyte, when we are purifying a metal, not just purification of metal, whenever we're electroplating, but in this case, it's purification of metals. The electrolyte must be one in which the metal in question that's being purified can dissolve in. So we need a soluble salt of copper in this case. So copper sulfate is already soluble, so we need not modify it. So for this one, we'll just write no modification required. And that's it. 3 more marks and a total of 15 marks. Hope you found this medley of questions to be, of use. Please leave a comment and share. And also be sure to check out all the other materials that are here on the channel. So as we normally say, and I mean, pun intended, copper later. It's been a lot about the copper in this medley. So all the best in your exams. Copper later.